Module 8.2. As a reminder, it's recommended to print the video script and annotate the script while watching the video for later use. Video scripts are available on Canvas. Module 8.2. How can we numerically describe the relationship between two or more variables? Previously, we saw different numerical summaries for a single quantitative variable such as a mean, median, and standard deviation. There are also numeric summaries to help us with two quantitative variables. Predicting the outcome of a variable. Often researchers would like to predict the outcome of a quantitative variable based on values of an explanatory variable. To illustrate this concept, we will consider the Happy Planet dataset. The Happy Planet Index measures what matters: sustainable well-being for all. It tells us how well nations are doing to achieve long, happy, sustainable lives. Data for 143 countries were collected. Included in the dataset is life expectancy for the country and a happiness score ranging from 0 to 10. Suppose a researcher is interested in predicting a country's happiness based on life expectancy. We can use a scatter plot to help us. To use the scatter plot to help us, we need a way to summarize the information contained in the plot. When the points in the plot have a linear pattern, we can use a regression line to summarize the information. Definition. A regression line is a line that best fits the data in a scatter plot. It is also known as a least squares line. When there is a single explanatory variable, the equation for this line can be written as follows. Y hat is the predicted value of the response variable. The hat on the y lets us know that it is a predicted y value. A is the intercept of the line. Notice A is a statistic because it will be calculated from the sample data. Some texts will also use the symbols lowercase b with a naught as the subscript, or b hat naught. B is the slope of the line. Notice B is a statistic because it will be calculated from sample data. Some texts will use the symbol b subscript 1 or b hat subscript 1. The regression equation can help us predict average happiness index score based on life expectancy rating. For the Happy Planet data, our response variable is happiness and the explanatory variable is life expectancy. To make the equation easier to read, let's replace y hat with happiness hat and x with life expectancy. The regression line becomes the following. How do we find the slope and the intercept? We will use software such as R or SAS to help find them. In Module 8.3, you will see how to do this. Using a computer, A is equal to negative 1.104 and B is equal to 0.104. Replacing them in the equation gives the following. We can use this equation to help us predict the happiness of a country with a life expectancy of 75 years by setting life expectancy equal to 75 and solving for happiness. This tells us that the predicted happiness score of a country with a life expectancy of 75 years is 6.65. Notice that the predicted happiness scores fall on the line. We can use the plot to predict the happiness of a country with life expectancy 75 years. We can find the prediction by drawing a vertical line at 75 years. Notice that the vertical line intersects the regression line at 6.65. This is the same predicted happiness index we got using the equation. The line and the equation contain the same information, but the equation will give you a more precise value since the line requires you to look at the graph and estimate the value. To find the slope and the intercept of the regression line, we need a way to compare the data we observed and the line that we summarize the data with. The observed value y is the response value observed for a data point. For example, each of the 103 happiness index scores in the data set is an observed y. The predicted value of y hat, is the response value that would be predicted for a given x value based on a line going through the points. For example, any predicted rating you could find using the line. The regression line, that is the line that makes the predicted closest to the actual values, is the regression line. Residuals give us a way to compare the observed y to the predicted y. The residual for each data point is equal to the observed minus the predicted. We can also say that the residual is the vertical distance from each point to the line. The goal is to make all the residuals as small as possible. We can do this by drawing the regression line, also known as the least squares line, which minimizes the sum squared of the residuals. Looking at the plot, here we have the distance from each point to the line as a residual. Since there are 143 data points, there are 143 residuals. Realistically, when we collect our data, there will also be limitations since we are only looking at a sample and not the entire population. Thus, we can never really know the true value of the response for each value of the explanatory variable. Instead, the true value, we rely on the values that we observe in our sample. Hence, we use residuals to estimate error. The error is the difference between the observed value and the true value. Simple linear regression defines a statistical model for a linear relationship between the response variable and the explanatory variable represented by the line, plus random variation, the errors. The statistical model is given by the following. Here, y is the response variable. Alpha plus beta x is the relationship between the explanatory and the response variable, and epsilon is the random error. Since the model describes a population, the slope and intercept are parameters represented with Greek letters. Using the data, the true values of alpha and beta can be estimated. These estimates are given in the regression line discussed earlier. Here, A, a statistic, is the estimate of the parameter alpha, while B, a statistic, is the estimate of the parameter beta. To use linear regression, we need to satisfy the following assumptions. The subject and the sample are independent from one another, and the errors come from a normal distribution with mean zero and constant variance. Regression is a wonderful tool because it can help us predict what happens when we do not observe every possible value of the explanatory variable. It is one of the most commonly used tools. As with any tool, we do need to make sure that it is appropriate to use. If you would like to learn more about regression, consider taking BST 681. Guidelines for using regression lines. One of the most important things is to plot your data before using a regression line. Regression lines require a linear association. A computer will calculate a regression line for you with any set of two quantitative variables with the same number of values. It is up to you to decide if it is reasonable to use the output. Regression lines are only useful when predicting values inside of the observed range of the explanatory variable. With the Happy Planet data, we would not want to use a line to predict the happiness of a country with a life expectancy of 95 years, because the longest life expectancy in the data set is 82.3. This is known as extrapolation. Outliers can have a large impact on the regression line. It is very important to make sure you do not switch the explanatory and response variables. The regression line will not be the same. The slope and the intercept of a regression line also hold valuable information for summarizing the variables. Each has its own interpretation. Slope is the predicted change in the response variable y given 1 unit increase in the explanatory variable x. For the Happy Planet dataset, the slope tells us that the predicted change in happiness index score for each additional year of life expectancy is a 0.104 increase. The predicted value of the response variable y, if the explanatory variable x is equal to 0. It does not always make sense to set the explanatory variable equal to 0. For the Happy Planet dataset, we do not have data at 0 years life expectancy. Therefore, it does not make sense to interpret the intercept since this would be extrapolation. Recall the correlation coefficient. There is a connection between the correlation coefficient r and the slope of the regression line. Here, S sub y is the standard deviation of the response variable, and S sub x is the standard deviation of the explanatory variable. For more information on regression, there are links in the notes to a series of videos from Khan Academy. Predicting the outcome of a dichotomous categorical variable. Often researchers would like to predict the outcome of a dichotomous categorical variable based on values of an explanatory variable. When working with an outcome that is dichotomous, categorical variable, linear regression is no longer appropriate. To motivate logistic regression, let's look at the association between birth weight and having a normal APGAR score. An APGAR score is a scoring system used for assessing the clinical status of a newborn. It comprises 5 components: color, heart rate, reflexes, muscle tone, and respiration. Each are given a score of 0, 1, or 2. Thus, this measure ranges from 0 to 10. A total of 7 or higher is generally normal, 4 to 6 is low, and 3 or below is critically low. Suppose we want to predict if a baby will have low APGAR score based on birth weight. Our 2 variables of interest are the following. Outcome variable will be 1 if APGAR score is normal, 0 if the score is low. The exposure or predictor variable is birth weight measured in grams. Suppose we naively fit a linear regression model. We would have the following scatter plot and the regression line. Suppose we want to predict the indicator of a normal APGAR score for an infant weighing 850 grams. Here we would find the predicted indicator of normal APGAR to be equal to 0.5181, but the outcome variable should be 0 or 1. In short, we can't use linear regression when the outcome is categorical because coefficient interpretations don't make sense, predictive values of the outcome are impossible, and it violates linear regression assumptions. Instead, we need logistic regression. When the outcome variable is dichotomous categorical variable, instead of modeling the 0-1 outcome itself, we need to model the log of the odds of having the outcome of interest. Recall from Module 5. Odds give us a way to compare the proportion with a certain outcome to the proportion without the outcome. The odds are the ratio of a proportion with an outcome to the proportion without the outcome. The log odds are given by taking the log of the odds. If we use linear regression to model the log odds, this is called logistic regression. Logistic regression relates the predictor variables to the log odds of the outcome, log odds of being in the category of interest. If y is the binary outcome variable, then let p be the probability that y equals the category of interest. The logistic regression model is the following. How does this help us make predictions? Plugging in the x value for the new subject, we can calculate their log odds. But in order to do this, we need to first review some notation and algebra reminders. In statistics, we use the natural log base e. So anywhere you see exp x, that means e to the power of x. If the log of y were to be equal to x, then y would be equal to the exp of x. And if the log of y over 1 minus y is equal to x, then y is equal to e to the x divided by 1 plus e to the x. These are what are commonly known as the logit and the xbit. So going back to how does this help us make predictions? Plugging in the x value for a new subject, we could calculate their log odds of an outcome, the odds of an outcome, or the probability of an outcome by using these functions. Continuing the APGAR example, we could use software to find the following. Suppose we want to predict the indicator of a normal APGAR score for an infant weighing 850 grams. Plugging in the x value for a new subject, we could calculate the log odds of having a new normal APGAR score as being negative 0.039, the odds of having a normal APGAR score as 0.962, and the probability of having a normal APGAR score is 0.490. Just like linear regression, the slope and the intercept of the logistic regression also hold valuable information for summarizing the variables. Each has its own interpretation. Slope, the predicted change in the log odds of the response variable y given a 1 unit increase in the explanatory variable x. For the APGAR dataset, the slope tells us that the predicted change in log odds of having a normal APGAR score increase for each additional gram of weight is 0.002 increase. Intercept, the predictive value of the log odds of the response variable y, if the explanatory variable x is equal to 0. It does not always make sense to set the explanatory variable equal to 0. For the APGAR data set, we do not have data at 0 weight, therefore it does not make sense to interpret the intercept since this would be extrapolation. Instead of log odds, we are usually interested in the odds. We could also have the following interpretations. E to the slope, the predicted change in the odds of the response variable y given a 1 unit increase in the explanatory variable x. For the APGAR dataset, the slope tells us that the predicted change in odds of having a normal APGAR score increases for each additional gram in weight is equal to E to the 0.002, which is equal to a 1.002 increase. E to the intercept, the predicted value of the odds of the response variable y, if the explanatory variable x is equal to 0. It does not always make sense to set the explanatory variable equal to 0, and for the APGAR dataset, we do not have data at 0 weight, therefore it would not make sense to interpret the intercept. Cautions in analyzing associations. When exploring the association between variables, there are common pitfalls that you will want to avoid. We are going to look at 3 of them. Extrapolation is dangerous. Extrapolation is using a regression line to predict y values for x values that are outside of the observed range of data. This is very bad practice. Be cautious of influential outliers. Outliers can be influential, which means they have a large effect on the results of regression analysis. To be influential, the x values is relatively high or low compared to the rest of the data, and it must fall quite far from the trend that is shown by the rest of the data. When these two things happen, the line tends to be pulled towards that data point and away from the trend of the rest of the points. Correlation does not imply causation. Correlation, association, does not imply causation when two variables are associated. Other variables may have influenced that association. We can never determine causation both slowly on a plot or regression line. We must know about the study.